Good afternoon to all of you. We'll just wait another minute or two as people join the webinar. So a very good afternoon again to everyone here. I'm very happy to see so many people join the webinar this afternoon, and especially pleased to introduce the speaker today, though to most of you, I think he would need no introduction. Dr. Hirali has been with schools of the Krishnamurti Foundation for several years, including as principal of Rishi Valley School, as director of the Sahyadri Center, and he's currently head of the teacher education program and based at the Valley School in Bangalore. He's also a long-time trustee of the Krishnamurti Foundation, India, and he's been very deeply engaged with mathematics education, again, for many, many years. And I'm really excited that these two parallel streams, in some sense, in his life and work, his engagement with Krishnamurti's teaching and his work in mathematics, are, I think, going to be brought together in interesting and profound ways in the course of this afternoon's talk. So his subject is Mathematics is Order, Holding a Mirror to Life. Mathematics is Order is a direct quotation from Krishnamurti. And as many of you would know, holding a mirror to life is an important recurring idea in Krishnamurti's thought. So over to Dr. Hirali to take this forward. Before that, I'll just mention that in case you have questions, and I hope there'll be many questions, please do type them into the Q&A that you'll find at the bottom of your screen at any time in the course of the talk, and we'll take up as many questions as we can after the talk is over. So the talk will be for about 45 minutes to an hour, and then we have till 5 o'clock. So over to you, Shailesh.
Thank you very much, Siddharth. And I'm happy to be here at this webinar to share my thoughts on this important question. And I'd like to just explain the background before I start a presentation. Krishnamurti used to hold meetings quite often with the teachers of the Krishnamurti schools. And among other things, he would discuss what it means to teach subjects in a way that addresses not only the intricacies and logic of the subject itself, but also addresses the human development of the child, so that both go together hand in hand. It's not just talking about the logic of a subject, but looking at the larger picture of the world and what is happening. So that's the background, and I'll start my presentation in that context. So I hope it is visible to all of you. And this is a statement that he made once in connection with the teaching of mathematics. He used to talk about the teaching of various subjects, including teaching of history and so on. But this particular statement stands out. Mathematics is order. Okay, so this is roughly what I'm planning to do in this presentation. So as I've written out here, he would often say in his conversations, that same statement, in fact, has come up quite often in his conversations. And I'm going to ask this question: what does the statement imply? And what are its deeper consequences? And specifically, I'm going to start by looking at what it means within mathematics. And that actually is the relatively easier part of this question. It is not so difficult to understand what the notion of order means purely within the domain of the subject. And then the larger question, which is, what are the deeper implications of this statement? Because after all, we are living in a world where there is a great deal of disorder. So there's a peculiar disjunction which we see already in front of us. On the one hand, we are dealing with a subject which typifies, exemplifies an extraordinary level of order. And at the same time, we are living in a world which is increasingly in disorder. And that disorder stems from us. It is not something foreign, not something alien. We ourselves are the generators of that disorder. And so how do we resolve this peculiar contradiction? This is a very important educational question to me. So let me start by just looking at a few simple examples. They are very simple examples which illustrate what order means. I'm going to look at 2 or 3 simple numerical instances, then something slightly more complex, which perhaps will be less familiar to some viewers. And then we will go into the question of the other implications of this quote. Let's look at something quite familiar to all of us, a calendar. That's the February 2026 calendar, which you see in front of you. And here's a simple, nice illustration of an order which you see. Look at these numbers in this left-hand corner where you see 1, 2, and 8 and 9, a 2 by 2 square. And if you multiply this, the numbers on this diagonal here, 2 and 8, and multiply the numbers on this diagonal, you get 2 times 8. And when you subtract it, you get 7. And then you take another square like that, this square, 3, 9, 2, 10. That means this square, the one next to it, okay, where you can see the mouse cursor moving. You multiply 3 and 9, you get 27, 2 and 10, you get 20, and the difference again is 7. And you see again that same pattern with the next set. You get 4 times 10 is 40, 3 times 11 is 33, and their difference is 7, and so on. So you see the same difference coming up again and again. Now, this is a very simple example of what in mathematics is called an invariant, something which doesn't change at all. And so it's an invariant is simply a quantity or a property in some cases that stays unchanged in different situations. And this is a fundamental aspect of mathematics. So the study of invariants in general lies at the heart of mathematics, because you'll find when you start studying mathematics, there are all kinds of invariants which are there in every situation, and they are a source of great delight to anyone who is exploring the subject. We discover them all over the place. Here's one which is there in a multiplication, a familiar multiplication table, which we all see. These are the numbers on one side here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and similarly on the top, and these are the products. For example, 3 multiplied by 5 is 15, 4 multiplied by 7 is 28, and so on. So here is the invariant that I'm going to show you. Look at any 2 by 2 square. For example, here, look at this 3, 4, 8, 6 here. You add 3 and 8 here, you get 11. And you add 4 and 6, you get 10. And you'll notice something about what the answers. Or look at another one. Look at the 16, 25. Let's see, where is 16 and 25? Here, this one here. 16, 25, 20, and 25. So if you add 16 and 25, it is 41, and 20 and 20 is 40. And again, you'll notice something relationship between the two products that you get there. And then another such situation where you are adding 16 and 27. Let's see now, where is 16 and 27? I have myself lost track of that. 18. Just a minute. Sorry, I've temporarily lost track of where this particular thing is. Now you'll find that
the third row, third and fourth row, or second and third row.
Oh yes, here it is. So yeah, at the top here, 16 and 27 is 43, 18 and 24 is 42. Again, you define that difference. So again, you find a difference of 1 happening each time. And that's a nice example of an invariance. And these two invariants, these properties are really quite nice to explain, particularly if you're teaching at the middle school level. Here's another one, again, dealing with a very familiar number sequence, which is the sequence of numbers. And you observe this property, which is often used at the middle school level to demonstrate a simple identity in algebra. That if you take any 3 consecutive numbers, take the square of the one in the middle and multiply the first and the third, So 2 squared minus 1 times 3, you get 1. Then take the next one, 2, 3, 4. So 3 squared minus 2 times 4 is again 1. Then take the next one, you take 4, 5, 6. So, 2, 3, 4. 4 squared minus 3 times 5, 16 minus 15 is 1. And similarly, you'll find you're getting 1 each and every time. So you see there's a certain invariance of this very simple sequence, familiar sequence. And here's a very similar looking property for a more complex sequence, which is known as the Fibonacci sequence, or in recent times, because of it has been discovered that it was known in ancient India as well. So it is known as the Virahanka Fibonacci sequence. So 0, 1, 1, 2, 3, 5. Each number is the sum of the previous two numbers. You have 5 is equal to 2 plus 3, 8 is equal to 3 plus 5, and so on. All right. And now if you take triples of these numbers at a time, 3 at a time. So take, for example, 0, 1, 1. If you square the middle one and then subtract the product of the outer two, here you'll get 1 squared minus 0 times 1, you get 1. Take the next one. 1 squared minus 1 times 2, this time you get a difference of minus 1, negative 1. Take the next one, that is 1, 2, 3. So you get 2 squared minus 1 times 3, the difference turns out to be 1. Take the next one, 2, 3, and 5. So 2, 3, and 5. So 3, I think I've written 4 by mistake. There's an error there. So 3 squared is 9, and 2 times 5 is 10. You'll get a difference of minus 1. Sorry, there's an error here. Please omit that. Again, you find this invariance, but this time you'll notice immediately that we have a slightly more complex pattern coming up. It's not just 1, 1, 1, 1, 1 as we got previously. It seems to be going through 1, negative 1, 1, negative 1. So that straight away shows that there are kinds of patterns, kinds of invariances which are of a more complex nature. But still, it has that character of invariance. So I'm going to now show you a couple of examples which are associated with the triangular numbers. So I'm going to first tell you what the triangular numbers are. They are simply numbers associated with these triangular shapes. So you start with 1, then you can have 3 dots or 3 marbles put in this triangular shape. You can have 6 arranged like this, 1 here, 2 here, 3 here. You can have 10, you can have 15. So you get these numbers as a result. You'll notice the numbers written at the bottom. So if you just keep continuing the sequence, you get this one. 1, 3, 6, 10, 15, 21, 28, 26, 36, and so on. These numbers are called the triangular numbers, and they have extraordinarily nice properties, a very rich sequence. So I'm going to show you a couple of things associated with these numbers. So here's a nice triangular party trick, which perhaps you may not have seen earlier. So take any number, for example, take 10, and write it as a sum of 2 smaller positive integers. So when I say number, I mean a positive integer. Okay, for simplicity, I've just written number, and write it as a sum of 2 smaller numbers, 2 smaller positive numbers, and record the product of those 2 numbers. For example, if you started with 10 and you wrote 10 as 7 plus 3, then you will record the product 21. Keep doing this for each of those smaller numbers. That is, whatever those smaller numbers you get, you split them into 2 then 2, and each time record the product. Continue like this till all the numbers left are just 1. So naturally, you're going to get ones in the end because you keep on reducing them. And at the end, find the sum of all the products that you get. And you'll find one very surprising fact, that no matter which path you take to reach the end, you get exactly the same sum. So I'll give you a simple example. Let's start with 6. So I'll start with 6 and write it as 4 plus 2. And then I record the number 8. 4 times 2 is 8. Then I split up the 4 as 3 plus 1. And I write, since 3 plus 1, 3 times 1 is 3, so I get a 3 out here. I hope you can see where my cursor is. So now I've got 3, 1, 2. And I split the 2 as 1 plus 1. So I get a product of 1 here. So now I've got the representation 3, 1, 1, 1. So now all these 3 are already 1, so they can't be split up further, but I can split this 3 as 2 plus 1, giving me one more 2 here. And then finally split this 2 as 1 plus 1. And that's, I get this thing. So I get all ones here. So I add up all these 8, 3, 1, 2, 1, I get 15. Now let's try another way. Suppose right at the beginning, instead of splitting it as 4 plus 2, I write it as 5 plus 1. So that gives me this product of 5. Then I write 5 as 3 plus 2, and that gives me a product of 6 out here. Then I write the 2 as 1 plus 1, and I get a product of 1 out here, and so on. I continue like this till the end, and you'll find at the end I have got these 5 quantities to add, 5, 6, 1, 2, 1, and they also add up to 15. Or I can do 6 as 3 plus 3. And when I go through this whole sequence, you will find you are adding up 9 and 2 and 1 and 2 and 1, and yet again you get 15. So each time you get 15. So again, a peculiar kind of invariance, which is much more tricky to understand. This is to try to analyze this problem and see why you get 15 each time. It takes a little bit of work. And it's not, then you notice something surprising here, that 15 happens to be a triangular number. Remember what we saw in the previous 1, 3, 6, 10, 15. That's the sequence of triangular numbers. So 15 is and it is the 5th triangular number. And you started out with the number 6. So this is something to take note of, whether it's something is it a coincidence? And it's an interesting question to ask, whether coincidences can happen in mathematics. Maybe they can, but to dismiss something as coincidence would be rather rash and perhaps foolish, because there may be a deeper reason for something turning out to be in some unexpected way. So this is a problem worth exploring. I'm going to show you another situation, which I call the pizza problem. So here you have a situation where these circles here just represent pizzas, or if you prefer, dosas. And I run a cutter through this pizza and keep dividing it into pieces. And each time I run the cutter through it, I take it completely from one end to the other end. It's not sort of half a cut, it's a complete cut. So it's dividing the pizza into 2 parts each time. But of course, those parts themselves may be parts of other parts. So you start getting multiple parts. So now just observe this. If I just run the cutter once, a single cut, I get 2 pieces, right? Then I run a second cut and I get 4 pieces. So the first cut and then followed by a second cut, and you'll notice that there are 4. Then having already run these 2 cuts, I run a third cut, and I end up, if you count carefully, these dots indicate what you should count them, you'll find that there are 7 pieces. So you got 2, 4, and 7. Keep those numbers in mind. Then now I'm going to add one more cut, and it becomes rather messy, but if you carefully count the number of pieces that you get, from 4 cuts, you end up getting 11 pieces. And from 5 cuts, now it looks quite a mess, but if you carefully go through the whole picture, you'll find you've got 16 pieces. Of course, please spare a thought for the person who gets that piece. It's a rather undemocratic way of cutting the pizza. Now look at what you've got. You've got a sequence. With 1 cut, you got 2 pieces. With 2 cuts, you got 4 pieces. 3 cuts, 7 pieces. 4 cuts, 11 pieces. 5 cuts, 16 pieces. A peculiar sequence. So where does that sequence come from? Now you subtract 1 from each of these numbers, and you will end up getting 2 minus 1 is 1, and then 4 minus 1 is 3. You get 1, 3, 6, 10, 15. So a strange occurrence of the triangular numbers inside this cutting problem. You get the T numbers all over again. And then how come? Where are they coming from? Is it again a coincidence? or is there some simple reason behind this? Now, the thing about mathematics is, really speaking, it's almost never the case that there are coincidences. There may be, as I said a moment back, but generally it is explainable in terms of some phenomenon which is already known. So you're trying to reduce a phenomenon to something of a simpler nature, then reduce that simpler thing to something still simpler, and so on. That's the normal, common way of doing it. So let me show you another such example, which is a very beautiful geometrical example, which is associated with the philosopher mathematician René Descartes, who discovered a very nice result concerning a convex polyhedra. And let me explain what this is about. So here it's about something called angular defect. Now, if you take a two-dimensional plane and draw a number of lines emanating from any point and add up all these angles, those angles add up to exactly 360 degrees. That's known. But if you take a three-dimensional situation, something where you have a number of planes joining up at a point, at a vertex, and you add up all the angles around that vertex, if you carefully add them up, you will find invariably that the sum is less than 360 degrees. This is for a normal, what is called a convex shape. Let's worry about these terms. And the deficit, by how much it is less than 360 degrees, is called the angular defect. That quantity by which it is less. So I'm going to show you a few shapes now. To start with, this is called the regular tetrahedron. It's like a little bit like an equilateral triangle, but in 3 dimensions. So the angle, if you consider each of these faces, each is an equilateral triangle. So every single angle is 60 degrees. There are 3 such faces meeting at each point. So they add up to 180 degrees, which means the angular defect at each vertex is 360 minus 180, which is 180 degrees. And since there are 4 vertices altogether, the total angular defect comes to 720 degrees. So note the computation. 180 is the total angular sum at each vertex. Then you subtract 360 minus 180 to give you the angular defect, and multiply by 4 because there are 4 vertices. So you get 720. Now let's take a regular cube, also known as a regular hexahedron, because it has 6 faces. Now, at each vertex, this is a 90-degree angle, right? Angle of each face at each vertex is 90 degrees. So the angular sum at each vertex, since there are 3, you'll notice at each vertex there are 3 faces which move, which meet. So you're at 3 times 90, which is 270 degrees. Then you get the angular defect at each vertex is 360 minus 270, which is 90 degrees. And if you count, there are 8 such vertices. So the total defect you get is 8 times 90, which is 720 degrees. Like last time you got 720, again you got 720. Now let's take this figure called the regular dodecahedron. It has 12 faces. That's why it's called a dodecahedron. And each face is a regular pentagon. So let's try to figure out the total angular defect of this one. So the angle of each of these is this regular pentagon. It's well known that each angle is 108 degrees. So the angular sum at each vertex, since there are 3 of them meeting at each point, is 3 times 108, which is 324 degrees. So the angular defect is 360 minus that, so 36 degrees. And now you may wonder how many vertices are there altogether? Well, there are 5 on the top here, and similarly 5 at the bottom. So that gives you 10. And if you carefully count, there are 10 on this equator. So there are 20 altogether. So the total angular defect is 20 times 36, which is yet again 720 degrees. Let's look at this figure, which is usually called the regular icosahedron. Here, it's entirely made up of equilateral triangles. There you have the top here, where you have 5 equilateral triangles coming together. So here also you'll notice 5 equilateral triangles coming together and so on. So the angle at each vertex, at each face of each face is 60 degrees. There are 5 of them coming together, so you get 300 degrees. So the angular defect at each vertex is 60 degrees. And this time there are 12 vertices altogether, giving you 720 degrees. So there's one vertex at the top, one at the bottom, 5 on this layer, and another 5 on the next layer. So 1, 5, 5, 1 adding up to 12, so you get 720 degrees. And finally, this shape, which is the truncated icosahedron, it's basically this shape where you chop off a little bit from each vertex. You sort of, okay, so what you chop off becomes this here, these chopped off pieces. And this is a very nice exercise to compute the total angular defect of this. Now you'll find at each vertex there are 2 hexagons and 1 pentagon. So the 2 hexagons contribute 120 degrees each, and the hexagon contributes 108. So that gives you 240 and 108 is 348 degrees. So the angular defect is 12 degrees. And here again, it's a bit tricky to figure out how many vertices there are, because that's itself a nice challenge to give to a child in middle school or high school, because you can't see all the vertices. They're hidden there. To try to figure out how many there are, you have to understand exactly how this shape works. But you will find that there are 60 of them, and that gives you again 720 degrees. So each and every time you got 720 degrees, and that's you end up finding a very nice example of invariance here, which is that the total angular defect of any convex polyhedron is 720 degrees. So now for my last example in mathematics, I'm going to talk about strings and compositions. And what is a string? A string is basically exactly like a word. You just have a string of letters. In this case, it will be a string of numbers, string of digits actually. String of numbers, sorry. So by a composition of any particular number n, what we are going to mean is a string or a word of positive integers which add up to that given number n. For example, these are the compositions of 3. So this one, you can have 3 just by itself. You can have 2 followed by 1, 2, 1. You can have 1 followed by 2, 1, 2, or 1, 1, 1. So there are 4 possible compositions corresponding to a sum of 3. You can convince yourself that there is no other, that those are all the possibilities. So notice 2 things. One is that order matters. 2, 1 is not the same as 1, 2. It's just like in a word. If you change the order of the letters, you get a different word. Here also you get a different string, and therefore it is counted differently. And secondly, the number is not specified. So you have here, there's only one number, 3. Here there are 3 numbers, 1, 1, 1. So we are not worried about how many numbers there are, but they should add up to some given number. So suppose you denote by this symbol a subscript n the number of compositions of n. That means so it counts the number of compositions of n. So a of 3 is equal to 4 because there are 4 compositions corresponding to a sum of 3. And the very nice problem to give to a student or to give to anybody is to find a formula for a subscript n. So let's try to generate a table of values bit by bit. So here's the table. So we start with 1, and there is just one composition of n. So I write a of 1 is 1. Then 2, well, what are the compositions of 2? You can have just 2 by itself or 1, 1, which means there are, and obviously there's nothing else. So there are 2 compositions giving you a sum of 2. For 3, we just saw it. We already know the answer. There are 4 compositions. Then for 4, let's see what you get for 4. There's 4 by itself. You have 3, 1, and then 1, 3. 2, 2 2, 1, 1, 1, 2, 1, 1, 1, 2, and then 1, 1, 1, 1. Now, just look at the list carefully, and I think you'll need to look at it carefully and convince yourself that we have not missed out anything. These are really all the combinations possible, all the strings possible. And you can various ways of checking that it's true. And if you count these, you'll find that there are 8 possibilities. Let's look at now the case for 5. You have 5, 4 followed by 1, or 1 followed by 4, 3 followed by 2, and 2 followed by 3, 3, 1, 1, 1, 3, 1, 1, 1, 3, 2, 2, 1, 2, 1, 2, 1, 2, 2, and then the rest, 2, 1, 1, 1, 1, 2, 1, 1, and so on. And here again, you have to look carefully, and you'll notice they have been arranged in a particular way that makes it easy to check and be sure that you have not missed out anything. Everything has been accounted for and nothing has been counted more than once. That's important to see. And if you count these carefully, you'll find you get 16. And now if you look at this sequence, it cries out, a pattern just cries out at you. And it appears that you'll notice that A of 2 is 2, A of 3 is 4, and this is what is called a doubling sequence. Each number seems to be double the previous one. So A of 4 is 8, which is 2 cubed. A of 5 is 16, which is 2 to the power of 4, and it looks as though A of n is equal to 2 to the power of n minus 1. And naturally, the question is why this should be true. And I'm not going to try answering that question here. It's a lovely problem to explore why should it be true and explain, giving a nice reason why it is true. It's a nice exploration. But this is an extremely nice example of an invariant pattern, something in which you didn't expect. It's sort of out of nowhere, this nice sequence comes out, 1, 2, 4, 8, 16. I'm going to look at another such example, which you might call an order version of the same problem. So I'm again going to look at compositions, but this time I'm going to allow myself only the use of odd numbers. So I don't allow any even number to be used in the string at all. So for example, let's look at 4. So what are all the ways of writing 4 as a sum of that string using only odd numbers? So I can't use 4 by itself because that's even, but I can write it as 3 plus 1, or 1 plus 3, or 1, 1, 1, 1. And that's it. There are no other ways of writing 4 as a sum of odd numbers. Just check, right? You can't use 4 itself. You can't use 2. So these are the only ways possible. So let's write B of n to be that the total number of odd compositions of that number. So that means, there's another error here. It should be B of 4 is 3. So not B of 3, sorry, there's a typo here. So there are 3 compositions, 3 odd compositions of 4. And now we want to find a formula for B of n. So let's try the same experiment as we did last time. Here is the values of n, the odd compositions, and the total count here. We start with 1. There's only one composition out here. Then for 2, the only composition possible is 1, 1. So again, we get a 1 out here. For 3, you can have a 3 or you can have a 1, 1, 1. So there are 2 compositions here. Then for 4, well, we just did that experiment. You have a 3, 1 or a 1, 3, and then 1, 1, 1, 1, giving you 3 such combinations. Then you try it with 5. You can have 5 by itself, or 3, 1, 1, 1, 3, 1, and 1, 1, 3, and then 1, 1, 1, 1, 1. So you can count, there are 5 such combinations. Let's do it for 6. Now we have to be careful we don't miss out anything. Maybe you can start with 5, 1, and 1, 5. then you have 3, 3, then 3, 1, 1, 1, 1, 3, 1, 1, 1, 1, 3, 1, 1, 1, 1, 3. And then finally 1, 1, 1, 1, 1. Again, I've missed out a 1. There should be one more 1 here. But if you count here, 1, 2, 3, 4, 5, there are 8 possibilities. And if we look at this sequence here, again, it cries out for a pattern. 1, 1, 2, 3, 5, 8. It's the good old sequence which we saw some time back, which we call the Virahanka-Fibonacci sequence, more familiarly known as the Fibonacci sequence. So it seems as though this is that number. And again, I am asked why. So I'm not going to explain why, because those questions have to be explored in a class. So I think I have given you a number of examples showing how invariants, how patterns arise in mathematics. They seem to arise just naturally and easily, spontaneously. They seem to just come out like, plants in a forest. There seem to be so many of them. The more you explore, the more such patterns you begin to find. Now I'm going to enlarge the question, because that's really the question. That question must be asked. What significance does order have? So from this point on, I am not going to be talking about the purely mathematical aspect of the question, but I'm going to try to look at the question in a slightly larger context and look at the significance of order and what it might mean for our lives, what it might mean for society. And I feel that this question must be asked. It is not enough to study a subject purely as a subject, any subject. That's not true only for mathematics, it's true for any subject. First of all, what do we mean by order in mathematics? When we use the word order, order normally means something which is very orderly, something which everything belongs together. Things fall together in place. There's nothing out of place. Everything is true, so to speak, in a straight line. So one statement you can see is nothing in mathematics is arbitrary. Once the axioms and starting the rules are fixed, nothing is arbitrary. If something is true, it is so because it must be so. There's really no choice about it. There's nothing arbitrary about it. Secondly, there's no clutter in mathematics. The more you study mathematics, the more you play with mathematics, you begin to see that it's a subject where there's no clutter, no excess, no waste. Everything belongs. Everything the proofs that you come up with, the properties that you find, they sort of belong to a whole. And there is a kind of austerity about it. When you say nothing, no excess, no waste, that indicates a kind of austerity, a kind of coherence. And isn't this really an illustration of what the word art really means? The word art, in its root meaning, the original root meaning of that word, is exactly what I said about order. Art, in its root meaning, indicates that everything fits together, everything belongs together. There is complete harmony between the parts. And mathematics seems to illustrate that. Complete harmony within the parts, between the parts, where everything finds its place, where everything is where it belongs. Now, it's important to take note of this characteristic of mathematics, that it's a subject in which there is complete harmony. There's a sense that everything falling into place, everything being in sequence. Then another very important aspect of mathematics is that there is no such thing as a contradiction. And this is one of the most vital principles of mathematics, in fact, the fact that contradiction is not permitted in the domain of mathematics. The subject forms an undivided whole. We simply cannot permit things in mathematics which contradict one another. That would be completely destructive to the subject. So much so that you have this beautiful quote from G.H. Hardy's book, A Mathematician's Apology, where he writes, he describes a certain proof in that book. And then he makes this commentary about that proof. He says, the proof is by reductio ad absurdum. That's the Latin phrase for, reducing something to the absurd, which is basically means proof by contradiction. So he says the proof is by reductio ad absurdum. And reductio ad absurdum, which Euclid loved so much, is one of a mathematician's finest weapons. It is a far finer gambit than any chess gambit. A chess player may offer the sacrifice of a pawn or even a piece, but a mathematician offers the game. This is a very beautiful quote, and it's a very revealing quote, because when he says a mathematician offers the game, it's like he's offering the possibility of a contradiction. And if the contradiction really were to come out to be so, that would end the spell of the subject itself. In fact, there's a famous story associated with Bertrand Russell. Some people associate it with Hardy, but I think it's Russell, where he demonstrates that if you have a single false statement which you accept in mathematics, then everything, you can use that to prove just about anything you want. There's some if there's time at the end, I'll share that episode with you. But this is a very fundamental aspect that you can, once you have a contradiction, it can be used to destroy the whole subject. Now, this again is a very important principle. Don't restrict it to just mathematics. Just think about it as contradiction is not permitted. So now it is time to move away from the domain of mathematics and ask, what does order signify in the larger context of life? And it is necessary to ask this because human beings are bringing about so much chaos and suffering and destruction in the world. So we have to confront this problem. It may seem odd, but we don't have a choice about it. That on the one hand, we are dealing with a subject which exemplifies order, which is such a beautiful illustration of order. And at the same time, we are living in a world in which we have generated extraordinary levels of disorder, exploitation, cruelty. It all comes from us. It's not the source of it is not some alien intelligence. We are the generators of that same phenomenon. So how are we going to reconcile all this? To talk about order and then to live in disorder? What do you do with this? So I'm going to read out one quote from Krishnamurti here. So he says, what do we mean by order? In the supreme sense, the universe has known no disorder. Nature, however terrifying to man, is always in order. It becomes disordered only when human beings interfere with it. It is only man from the beginning of time who seems to be in constant struggle and conflict. The universe has its own movement of time. Only when man has ordered his life will he realize the eternal order. Why has humanity accepted and tolerated disorder? Why does whatever man touches decay, become corrupt and confused? Why has mankind turned away from the order of nature, from the clouds, the winds, the animals, and the rivers? So there's a very serious question being asked here. Why have we human beings turned away from the order of nature? When it says here, in the supreme sense, the universe has known no disorder. Nature, however terrifying to man, is always in order. What has made us move away from this? What is it in us? It's necessary for us to come to terms with our own essential disorder. Now, just in passing, I would like to make a comment here, which may slightly be surprising. The use of the word terrifying. nature, however terrifying to man, is always in order. And in this context, a beautiful example of terror, is this very famous poem by the poet William Blake called Tiger, Tiger, where he talks of the first verse of this is Tiger, Tiger, burning bright in the forests of the night. What immortal hand or eye could frame thy fearful symmetry? And the poet is wondering here, that this poem is not just about the tiger. It's about nature, really. It's about nature and its extraordinary symmetry. And when you start looking at it, the sheer power of nature, the sheer power of the forces that you experience within nature, once you begin to understand them, they are truly terrifying. If you get that sense when you study a subject like astrophysics, for example, immense, gigantic energies. Just yesterday, I was reading about a situation where what happens when two supermassive black holes, which are at the centers of galaxies, if they ever come into contact and collide with each other, and the kind of energies which are generated by that collision are simply unbelievable. This is simply beyond even our imagination. So there can be something truly terrifying about nature. And nature is the source of that order. However terrifying, it is always in order. So if you're not familiar with this particular poem, I invite you to read it. It's a very beautiful poem. So let me go on. What can we learn from mathematics for our own lives in the larger context of society? In mathematics, first of all, you cannot cheat reality. You cannot manipulate truth. There's no such thing as my truth or your truth or relative truth. There is only truth. Just absorb this for a minute. There's no such thing, these phrases often come up in social context. My truth, your truth. This is true for me. It's true for you, that kind of thing. But in mathematics, there's no such thing as my truth or your truth. There's only something true or false. There is no place for belief. There is no place for opinion. There's no place for ideology. There's no place for authority. Some of you may know that familiar statement made by Galileo about authority. He himself had a conflict during his lifetime with the church about a statement that he made. So he was well placed to make a comment about authority. That in matters of science, he was referring to science, authority has no place. Even less so in the case of mathematics. There's no place for authority. If something is true, it is true because of itself and not because of any authority, however big the person may be. That's not what makes it true. There's no place for contradiction. That observation was made a minute back. So mathematics thus exemplifies order. And it's important to see that that order is not imposed by any agency, which means it is not brought about by control. It is not brought about by some rules which you impose on it, some kind of a structure which is imposed on the outside. It seems to arise from its very nature. Just look at those examples which we saw there, which we saw at the start. The examples of the sequence of +1 and -1 in the case of the Fibonacci sequence. It seems to arise from within itself. It's not that somebody wanted it that way. So this is, what kind of order is it which arises from within? So the question naturally is, the reality for us is that we are not in order. So on the one hand, we are dealing with a subject which has extraordinary levels of order, but we ourselves are in disorder. So what is order from within? Is there such a thing as order from within? Is there such a thing as inner order? Not order brought about by an outside agency, which means order imposed through control, order imposed by authority, order imposed by some ideology. What is order that arises from within, from our own understanding, in which there is no element of control in it? So I have tried to explain in the next paragraph the reason for asking this question. You must ask this because order in mathematics may be extraordinarily beautiful and a source of wonder, something to celebrate. And it truly is something to celebrate because there are so many such beautiful results which you can find in mathematics. But it will not have deep significance if inwardly we human beings are confused and disorderly and bringing about further disorder and conflict in the world. And the reality is one of disorder and conflict. Of course, this statement, you might, if you reflect on it, has nothing to do with mathematics per se. It is true of many other subjects also. Order in art, or there's so many things. You can have beautiful sculpture, extraordinarily beautiful sculpture, and you can marvel at it, celebrate at the beauty of it. But what is the significance of it if we continue to live in a confused and disorderly way and bringing about only further disorder and conflict? It sounds like a contradiction. The very thing that is not permitted in mathematics, we seem to be permitting it in our own relationship with mathematics, that we live in contact with these two. So there's peculiar difficulty out here. So what is this disorder that we are talking about? When we say we are living in disorder, in fact, you will find if you start examining it, that there is disorder at every level of human existence. The contradicted desires and the operation of will. When we are powered by willpower, inside us we are trying to control ourselves. We are battling one part of us, battling another part. The whole problem of will, identification with various ideologies and labels leading to fragmentation, the problem of comparison and conformity and imitation, and therefore hypocrisy, the problem of ambition, the problem of fear. Fear is the most direct demonstration of disorder. And you'll find, if you examine it, inner disorder inevitably leads to outer disorder. When there is inner disorder, ultimately it expresses itself in all these terrible ways: war or destruction of nature, conflict with nature, huge levels as they are at present of poverty and corruption and human exploitation. Outwardly, we may look organized. There may be civic order in many countries, good health systems, good roads, and so on. But inwardly, we see fragmentation and contradiction at every level. Here's a quote from the great physicist David Bohm, great quantum mechanics expert, who writes here, "We are faced with a breakdown of general social order and human values that threaten stability throughout the world. And existing knowledge cannot meet this challenge. Something much deeper is needed, a completely new approach. I am suggesting that the very means by which we try to solve our problems is itself the problem." And a statement by Albert Einstein here, when he says, "We cannot solve our problems with the same thinking we used when we created them. Of course, this is a translation of something he wrote in German. And both these individuals, who, by the way, worked together, they had a professional association. They are suggesting that the very apparatus, intellectual apparatus that we use to analyze the world itself may be the cause of all the difficulties we see around us. And therefore, we cannot solve those problems using those same techniques. Here, Krishnamurti says, what your daily life is, society is. Society is not different from you, from what you are and what you have been. That is the community in which you live. Social disorder exists because you are disorderly in your own life. Order cannot come. Please note this. This is a very important point. Order cannot come about through intellectual organization, through a plan. We have tried this for thousands of years. So many have endeavored to create a new society, a new way of living, and they have all failed because they build on a formula, on concepts, or an ideology. And you may wonder, what is the basis of making this statement? We have tried this for thousands of years. So many have endeavored. Well, historically, if you actually look for examples, there are any number of them. You'll find. Maybe if there is time later, we can start showing some examples. Many of the famous political revolutions that have happened in history are of this kind. Now, what is the source of order? We don't quite know. Disorder is very familiar to us, but we don't quite know where order comes from. Generally, social order comes about through a system of reward and punishment, or everyone promises to adhere to some ideology. And underneath this, you'll find underneath that layer, there is fear. And ultimately, that whole experiment collapses because of that. Is there another kind of order? Order that comes about when there is the understanding of disorder, and when there is affection and clarity. Such clarity brings about its own order, precision in thinking, staying true to facts, the art of listening to another human being, which means giving a person complete, undivided attention, humility. That all that comes about when there is that kind of clarity, which comes about when there is the understanding of disorder. And there's a curious statement which Krishnamurti made here when he says, it is strange how, when one is clear within oneself, whatever may happen is right. We'll see if we can understand that later. But what is the source of clarity? So there's a bit of a mystery here, or not a bit of a mystery, perhaps that's the major mystery. Where does order come from? What's the source of order? So I'm going to end this with a few quotes. Here is Krishnamurti again. He says, let's say I'm a teacher of mathematics. Mathematics is order, infinite order. Order is the universe, is intelligence. Order is not static. It is a living movement. Our life is movement, but we have brought about disorder in our life. So I am going to talk to the students not just about mathematics, but about order in our life. Negation of disorder is order. A human being confused, disorderly, uncertain, in trying to establish order creates only more disorder. I see this very, very clearly. So I'm going to help the students. And in helping them, I am helping myself. That order cannot be pursued as you can pursue mathematics step by step. So the first thing to realize is that thought, do what it will, can never bring about order through legislation, through administration, or compulsion. Order is independent of thought. Thought cannot put together order. The more it attempts it, the greater the confusion. Mathematics is not disorder. Mathematics in itself is basically order. Thought is capable of seeing the order of mathematics, but this order is not the product of thought. One can see the great majesty and beauty of a mountain, but the human being who sees it may have no dignity, no majesty, no beauty. I must study order and disorder before I can discuss it with my pupils. The study of a book on any particular subject is very different from the study of myself, who is disorderly, confused. The book reveals things phrase by phrase, chapter by chapter, coming to some conclusion or the other. The book is visible, and one can spend perhaps years on the subject of the book. But I am not just studying just any book. I am studying a book that has no print in it, one which cannot be read through another's eyes. So I must find out how to study it. Here, of course, he is saying the book is myself, studying the book of myself. Because to understand, or you can't talk of order till I have understood disorder, which is me. And he says, adds here, the important thing, if we are to understand the cause of confusion, is self-knowledge. Without understanding oneself, there cannot be order in the world. Without exploring the whole process of thought, feeling, and action in oneself, there cannot possibly be world peace, order, and security. Therefore, the study of oneself is of primary importance. So I think one thing that comes out from this is that to talk about order, to try to create a model of order, to try to visualize it, to try to create a picture of it, and then say, I'm going to go there, is essentially a mistake. Because that is exactly what has been done in all these failed experiments of looking for utopia, all these revolutions of the past. Unless we take the important step of working on our own disorder, understanding our own disorder, and putting an end to this whole process of generating disorder, which involves understanding ourselves to a very, very fine degree, we are just going to continue adding to disorder. So this question really has to be gone into. Let me just end to the last slide. Okay, so it's time to close. I hope I have been able to share not only the joy to be found in mathematical order, but also what it may be pointing to, which is something of grave and vital importance in our lives, and the great beauty and mystery of order that has no cause, that comes about naturally and spontaneously when there is the understanding of disorder. And if you really have to go into it more deeply, we inevitably have to come and deal with the question of meditation, which all ancient religions have addressed in their attempt to create order, all kinds of practices. And similarly, the notion of dharma, which is also something about the order of the universe, which is the order within us. So all these need to be looked into. So I won't be able to, there's no time to go into that. So I'll end with this quote, which is again a quote about beauty. It's fitting to end with this little verse of Keats, because Keats was one of the favorite poets of Krishnamurti. And he said, a thing of beauty is a joy forever. Its loveliness increases. It will never pass into nothingness. So let me stop here. I have not perhaps left very much time for questions.
Thank you. Thank you very much, Dr. Shirali. That was very, very engaging. And I'd like to plunge straight into the questions. There are quite a few that have come. And I'd perhaps club together 2 or 3 questions which relate directly to education, since, our underlying theme here is, of course, education. So one question here is, order outside creates order inside, and vice versa. Where to start? How to deliver this message to the younger generation? And I'll take up a second question, which is how can we use mathematical order to develop resilience in children when so much is driven by social media? So, would you like to
Yes,
address this?
I think one of the very important generators of disorder is our own insecurity and our own undeveloped nature. We are our own tendency to conform, to imitate, to all the time look for approval from others. And when our own capacity to listen and experience the world is not really isn't given a chance to even develop, and we're always going to be leaning on the approval and views of others. And I think this contributes to a great deal of insecurity in us. We are too weak, and therefore we become prey to whatever happens in social media. We are prey, completely at the mercy of the opinions of others. I think it's not merely in the mathematics class, but in the class in general, to develop as a whole human being, to be able uh, to see things with one's own eyes, to see the difference between what one is seeing and what one is just reflecting another person's views, another person's opinions, which I am filled with. So that has to come out through conversation between the teacher and the student, an understanding of one's own, how one looks at something. So an essential inner fullness which has to grow through the one's experience of the world. I think vast numbers of children across the world are given very little opportunity to grow in that sense, because we are just filling ourselves with views and opinions from just gathered from others, from the outside, not realizing it. And that's part of the generator of disorder. So again, there's a lot more to explore in this, but I'll stop for now.
I was just wondering, in your many years as an educator and especially teaching in schools, have you found that there are ways in which you've been able to approach some of these issues head on? So, for example, you spoke about the contrast between order in mathematics and disorder in human nature, though there's order in nature. And a related question I have is, how does this become something intrinsic to the learning of the child and not merely a set of received ideas? Because this too can become like a theoretical sort of discourse. How does it become real?
It's obviously a challenge, but I think one integral part of it is becoming aware of one's own inner motivation in doing something. What is driving one forward in any particular direction? Why are we wanting to do it? Am I in a state of competition as a student? Am I trying to compete with somebody else? Make sure that I am noticed in front of the other person. Is that or I'm actually interested in exploring the fullness of a question, and therefore giving myself space for that exploration, for growing within that inquiry. I think this is a very tricky issue, because we are so heavily influenced by our surroundings, and the pressure, the peer pressure, the pressure of adults, pressure of wanting to fit into a particular situation, the lack of security that we feel. So this pressure is very difficult to face. Most children find it break under that. That pressure simply breaks you. You're not able to stand up to that pressure. So I think one very important thing about that a teacher can do is to take the questions of a child seriously. When a child is asking a question, to actually attend to that child, and so that the child has the opportunity to really develop that question, to explore and understand wherever he or she stands, understand the difficulties, because otherwise being caught in that uncertain state of trying to fit into the pace set by somebody else, it's a very basic problem which children are going to be caught in right from the beginning. And it's the source of, I think, a lifelong problem if that is not addressed, of being able to live and ask questions with a sense of leisure, with a sense of space, not feeling rushed by the competitiveness of whoever is around you or the demands of the immediate surroundings. That ability to ask questions is something that needs to be taken as seriously as possible. The space for asking questions, the space for exploring a question, the space for exploration in general, not just in mathematics, but in life. And not allowing a person to get an easy answer to a question, to just sort of quench somebody's curiosity, to quench a question and to destroy it in the process, to actually give a chance for that question to grow, not just immediately give an easy answer and kill it in the process. I think that is an important thing, because in the larger life situation, when you have a serious difficulty, to simply find an easy solution for it may be very tempting, especially when somebody is in pain, experiencing sorrow. Finding some solution to it can just seem to solve the problem, but we may be actually doing a disservice in the process by you're not allowing the opportunity to really come into contact with the issue and to discover for yourself what is the nature of the problem. So there's something common between questioning within a subject here and in a life context.
I think one thing which is implicit in what you've just said is that the mathematics class doesn't end in the math classroom, because it sort of it spirals outwards into a number of questions which one needs leisure to pursue, and they are questions that are connected with human life. And so I think in schools, to break down this barrier between life questions and academic questions, and to find ways of seeing those connections at all times. But of course, one of the challenges we face as teachers, and especially with older children, is that we are always under pressure of time. You have to complete a curriculum, there are exam needs to be fulfilled. But then from what you were saying, I think these conversations happen in the sort of spaces between, where you can create that space for exploration.
Yes, we can't wish away those problems. They are there. We have to deal with them. If there are examinations, we have to deal with them. But it's important not to lose sight of problems that exist at a larger level, deeper problems, because they are not going to go away. And they are problems which can become personal problems, which, very, very easily. It's not as if one just escapes from them by not looking at them. I think for too long, we have made education into something quite narrow, merely develop the intellectual abilities of a child, and so that the child doesn't really come into contact, doesn't really grow up as a full human being. The intellect is tremendously developed, but not the emotional capacities of the child, the ability to look at something with sympathy, with affection, and let clarity come about as a result of that. So that perhaps is, though it was not mentioned, is one of the great examples of disorder, that our existing education system develops one side of us so strongly that our intellects, our abilities, skills, and so on are very highly developed. But the rest of us, the rest is completely untouched. Our ability to listen to one another, ability to listen to another human being, ability to feel what someone else is feeling, our relationship with life, with nature, with animals. So that's itself a very basic source of disorder, I think, that we have separated out the intellect and given such huge importance to the intellect. So that very word order, when we say mathematics is order would indicate that everything, all the components are in harmony. They fall together into a whole. But we have not done that in education. So there is a fundamental denial of that principle of the fact of order at that point itself, when we simply address the intellectual side of a child and neglect what is the vital aspect of humanity, the sense of being a whole person with the capacity to feel, to capacity to understand another human being or an animal. So that needs to be explored, I think, this question. How it can be done in the existing system, it may be difficult. The way our education system is constituted, obviously, it becomes quite difficult. It is so one-sided, our education system. So that's there.
Can I ask another question?
Yes,
So
please.
here's a question about the nature of mathematics, which is, what is it to say that mathematics is order in light of the fact that it is a product of thought? Now, that's a cryptic but intriguing question.
Well, the answer is that nobody quite knows where, though it is the product of thought. When we say that, we don't quite know whether we are, it's a huge point of debate within the world of mathematics. Do we discover mathematics or do we invent mathematics? If we discover it, it would imply that it sort of exists somewhere, as though it is somewhere hidden behind a rock, and we only have to uncover it. But the real experience of anyone working with mathematics is that it does seem to have that nature. It, patterns come up which you never put there in the first place, and order, relationships get discovered which don't seem to have been put there by anybody. So it's not, we don't quite know. There is a great mystery about that order. We don't know the source of that order. So it cannot be given some easy description that it's all the product of thought. The order of mathematics may have some deeper relationship to do with the very nature of the universe itself. We don't quite know. But when we are in contact with that, we to explore it further, yes, we use the instruments of thought, the analysis, verbalization, our capacity to use symbols. But where all that comes from, well, there is a bit of a mystery about that. So to me, the question really is, what is our relationship with order in general? What about the order of nature? We don't quite know. The order within nature is something so complex. We don't quite know how it works. It's not as if there is some agency behind it, and yet things seem to have some extraordinary harmony behind them. Is mathematics also of that kind? Something which is there in the very nature of things, it's sort of there in the very structure of things themselves, of space and time. So the answer is I don't know. But safer to give that answer. It's a very complex question.
Right, yeah, about whether mathematics is out there or whether it's been created by human thought. But I'd like to ask you one more question, since again, to keep the focus on education. This is on pedagogy. Problem solving is emphasized along the way somehow, and at some point very easily, it becomes the singular focus of mathematics. This is in conflict with order. In the pursuit of math, how do we as individuals and as educators accord problem solving its place and not be defined by it?
I think problem solving is an important component of math education, provided it is really part of why we are doing it at all. If it's merely a tool for exploration, if it's a way of exploring how concepts relate with one another in ways that become apparent only when you are actually grappling and struggling with a problem and begin to see in the process the relationship between parts which weren't visible when you just took one casual look. So that act of grappling and wrestling with a challenging problem is tremendously educative, provided that is the actual way in which it is conducted, that it is done for the purpose of discovery and exploration. But if it is merely there for competitive purposes, for one person to try to race and outrace the other person who manages to solve something first, I think that is a complete destruction of that whole idea. But otherwise, problem solving offers a wonderful opportunity for exploring and understanding relationships more deeply. And that very notion of order begins to fill out in the process. You see relationships which you never suspected, and they begin to emerge. And then you begin to find ways of justifying and proving them. But you can also destroy it in the name of whatever competition.
I suppose also, because I remember when, attending your classes as a student, and very often you would direct us to pursue something, to inquire into a problem, try and find out if there were patterns and so on, which was not strictly problem solving. Of course, we did solve problems as well. But I suppose this way of approaching mathematics as something open-ended that needs inquiry and discovery is also something which perhaps builds our capacity and stamina for inquiry in other areas as well, into human nature.
That is absolutely so.
Right.
Yeah, how to inquire into something in an impersonal, in a way that is not done for some selfish purpose. Simply, you're inquiring to find out the truth about something. I think it's a very important experience which a child must go through, that because there's great beauty in exploring something and slowly finding things emerging out of that exploration. It's exactly like growing something in a garden and you begin to see out of nowhere something coming out of the soil. And the same thing can happen in this mathematical context. You'll find unexpectedly some relationships are beginning to sprout, which you never even dreamt that of about. It's a great pleasure, and uh, it also begins to contribute to your sense of yourself. That we were talking some time back about how undeveloped one can be if one is always living on the views and opinions and observations of others. Somebody has told you this, therefore yes, it is so. We just absorb and live on the words of others. But when you yourself discover some phenomenon, it's a tremendous thing. And if that same thing, if it happens in the field of exploration of oneself, it even more so, to actually read, as metaphorically speaking, what Krishnamurti talk, reading the book of oneself. It's a great challenge to be able to read that book, which as he says, cannot be read with another person's eyes, another person's intellect. It has to be read through our own great capacity to attend and listen. So all this, becomes, it's a great opportunity to learn.
Yes, thank you, Shailesh. But it occurred to me also that one of the great difficulties when, or let's say the disjunctions between, reading mathematics or inquiring into mathematics and inquiring into oneself is that very often when we are inquiring into ourselves, it happens in situations of pressure, stress, there's something disturbing us. And, that disturbance itself becomes like a tinted lens, and it becomes difficult to see clearly because there's so much anxiety about that disturbance. But yet I think it's a wonderful parallel that you've drawn. And but it's actually 5 o'clock, but I'd like to bring one last question. There are several other questions. Unfortunately, we won't have time. And this question is also about the parallel between mathematical systems and let's call them human systems. And I'll just read the question. Order in mathematics happens because of sound axioms and rigorous reasoning. This order is only within a system, right? There may be perceived disorder between two internally consistent systems, such as Euclidean and non-Euclidean systems. In human beings, even the seemingly consistent people seem to be going between two systems internally. Is the key then to examine our basic axioms? So I think the question is building or taking further this metaphor between the bases of mathematics and human nature and contradictions.
Well, I think there is a slight difference here. It is true that in mathematics you can have different axiom systems which don't go together. You either choose this or you choose that. You don't choose both at the same time. But contradiction within human beings is not of exactly the same kind. Contradiction within human beings happens when we are divided within oneself, within ourselves. I simultaneously want something and I want its opposite at the same time. It is not so much of an axiom system, but our desires are themselves contradictory. We simultaneously seem to desire two things which just don't go together, which contradict one another. We want, for example, we may want peace, we want a harmonious atmosphere around us, but at the same time, we are ambitious, we are greedy, avaricious. We want something which obviously goes against that peaceful atmosphere. We simultaneously want both of these. And then it becomes like a battle of one side versus the other side. At one point, one side dominates, at another point, the other side dominates. So it is, the problem is not one of a logical inconsistency. The problem is that we have divided ourselves into contradictory parts. And unless we realize this, the nature of this contradictory division that we produce in ourselves, we will continue generating disorder. This is one of the sources of social disorder, how internal disorder spills over and becomes external disorder, ultimately war and so on. So, but unfortunately, I mean, I think one needs much more time to discuss this question. Ideally, it should have been face to face. So I'm sorry for that. I'm not fully able to address this, but I don't think at some point the parallel may not be exactly there. It's because the nature of contradiction in human beings is that of one desire trying to overcome and crush another desire. And this is something which we have to really examine.
Thank you. Thank you so much, Shailesh. That was your presentation was a thing of beauty, to quote Keats again. And I think we could have gone on for another hour. There are several questions. My apologies to all those who've answered questions that we haven't had time to take up. I do hope you'll find ways of exploring these questions in other ways. Some people in the chat have asked about where these webinar recordings can be found. And if you just look up Krishnamurti Foundation webinars on education, you'll find the recordings there. This particular session, it'll come there after a few days. Thanks all who've participated, and thank you for the many questions. I think we'll call it a day. Thanks again very much, Shailesh. That was a really rich and wonderful session.
So, thank you, Siddharth.
Good evening to all.
Thank you all members.